Hey guys, welcome back to chapter 10. So this first slide I'm going to show you is something I forgot to show you in the previous video, but it's a nice little summary slide for all of our simple gas laws, and then it has the ideal gas law on there as well. You'll see something similar to this on your exam cover sheet or on the formulas page for your final. All right, so we're going to dive into the next topic in chapter 10, and this is combining stoichiometry and the ideal gas law. So really bringing a lot of skills full circle. So we're just going to dive right into a problem and work our way through it. I think it's the best way to introduce it. So oxygen generators in some airplanes are based on the chemical reaction between sodium chlorate and iron. So sodium chlorate is probably not something you're familiar with. This right here is sodium chlorate and iron. The result is O2 is blended with cabin air to provide 10 to 15 minutes of breathable air for the passengers. Very, very interesting question that we would want to be able to answer. How many grams of the sodium chlorate are needed in a typical generator to produce 135 liters of O2 gas at 1 atm and 20 degrees Celsius? So just thinking about this problem, it's a very useful one. So somehow engineers came to the conclusion that 135 liters of oxygen gas would be needed to provide that 10 to 15 minutes of breathable air for its passengers. So since this is our target, this is how much they need. It would be really, really nice to know, well, how much of the sodium chloride are we going to have to pack in order for the reaction to make this much oxygen? And with airplanes, excess, you don't really want excess of anything. It's carrying a lot of things through the air. You want to have a precise amount of each of your reactants. Okay. So let's take a look at the information that's given. So how many grams of sodium chlorate? So that's our ultimate destination. So ultimately, we're going to want to solve for grams of this sodium chlorate. But let's take a look at the information we're given. We're given the volume of oxygen. We're given the pressure at which oxygen is, and we're given the temperature of that oxygen. Okay. So we need to find a way to get from oxygen, which is the information that's provided in the problem, to sodium chlorate, which is the information that it's asking about. That's where the stoichiometry comes in. So remember, stoichiometry would allow us to change from units of oxygen back to units of sodium chlorate. So that's the stoichiometry piece, and that should be a little bit of a review piece at this point. The hard part is going to be getting from this information of liters and ATM and pressure and temperature. So getting all of that information into a form where we can go from oxygen to sodium chlorate. So what unit do you suspect we will need to be in order to do stoichiometry? So what unit do we need to eventually get to? Yeah, we need to get to moles, right? Because this is a mole to mole ratio. So if we can get to moles of oxygen, then we just use stoichiometry to get to moles of sodium chlorate. And then at this point, we're experts at going from moles of sodium chlorate to grams of sodium chlorate, right? So this is where the ideal gas law comes in. So we're given volume, pressure, temperature. Well, that's a lot of the things we need in this equation. So we're given volume and pressure and temperature, and that's a constant. Oh, look, we can solve for moles. Okay. So before we dive in, let me just talk generally about this problem. We're going to use the information given about a gas to solve for moles of that gas. Then we're going to go from moles of that gas to moles of something else in that equation. And then if it's asking for grams, we can go from moles of that something else to grams of that something else. Okay, so let's dive in. All right, so we know the first step is going to be ideal gas law. So PV equals nRT, and take inventory of what we know and what we're trying to solve for. All right, so let's click back here. We've got 135 liters. That's our volume. Oops. We've got 1 atm of pressure. That's our pressure. 20 degrees Celsius. And then the R is a constant, 0.082 atm, liter, mole, and Kelvin. Okay. And N is what we're solving for here. Only one conversion that we need to do. So pressures in ATM, that's done. Volumes in liters, that's done. Oh, temperatures in Celsius. So we need to do the conversion. Remember, it's temperature in Celsius plus 273 will give us Kelvin. And let me just erase. Yeah, I'll cross it out. So this is 293 Kelvin. Okay. So now it's a simple plug and chug to get us to moles. So plug in what we know. So 1 atm, 135 liters equals N, 0.082 atm liters, mole Kelvin, and 293 Kelvin. Okay. So the first thing I'm going to do is I'm going to multiply over here and get rid of those Kelvin. So Kelvin on top, Kelvin on bottom, multiply these two numbers together. So that's going to give me 0.082 times 293. And I'm going to have 24.03. And we're left with atm liters over moles. And I didn't do anything over here yet because I like how units shake out. Okay. Now to solve for moles by itself, I'm just going to divide by 24.03. And on top, on bottom, that cancels. Whatever I do to the right side, I also need to do to the left side. And here's where we see those units shake out. So liters on top, liters on bottom, ATM on top, ATM on bottom, and we're left with moles. Okay. So plug that into our calculator. 1 times 135 divided by 24.03, and we get 5.62 moles. All right, so I'm going to start a new slide. So we're going to do 5.6, let me get this right. Yep, 2 moles of oxygen. And I'm just going to do a mole to mole ratio to get from moles of oxygen to moles of sodium chlorate. Okay. So to do that, I go to the balanced chemical equation, and I see that it's a 1-to-1 ratio. Not always going to be that way, but it is for this problem. So the coefficient attached to sodium chlorate is 1. This coefficient attached to oxygen is also 1. So it's 5.62 moles, and we've changed the units to sodium chlorate. The problem is asking us for grams of sodium chlorate. So it's not going to be very useful to say I have this many moles on my airplane. We'll have to do it in grams because that's something that's tangible to measure. So now just a quick moles to grams conversion. So 5.62 moles of sodium chlorate. I got moles on the bottom. grams on the top. And, oops, and NaClO3. In 1 mole of our sodium chlorate, we're going to have 3 oxygens, which is 15.999, plus a chlorine, which is 35.45, plus a sodium, which is 22.99. So this has a molecular mass of 106.44. Multiply across the top, divide by the bottom. So 5.62 times 106.44 divided by 1 means that I need to put 598 grams of sodium chlorate on my airplane in order to make 135 liters of oxygen. Super fun problem. Combines a lot of skills that we've worked on all semester. Hopefully these skills are becoming a little bit more intuitive, a little bit faster. Certainly going to see another problem like this on your final exam. I hope you guys found this helpful.